So the very first type of piecewise interpolation we're going to look at is piecewise linear interpolation. So we're going to always have the same setup where we have data points, and they're labeled t0, y0 through tn, yn. So there are n plus 1 given data values, and we want to find a function that interpolates them, and piecewise linear just puts a linear function on each piece, so you just connect the dots. So the idea is that between tk and tk plus 1, the interpolant p of x is a linear function. And we could write down the formulas for that line. There's nothing special about that. Instead, I'm going to suggest that we can write p of x in a way that's going to be very important because it generalizes to a lot of different things. So we're going to seek to write p of x in this form as the sum of, as a linear combination, I should say, of some particular functions. All right. So the ck coefficients here are determined by the data. The hk's are determined by the t-values. All right, so in this case, we can, again, it's easier to define things with a picture in this case than it is with formulas. So here are our t-values. This is the y-coordinate. So if we have the value 1 at one of the nodes, and then 0 at all the other nodes. Oops. So 0 at all these nodes. Okay, so in fact, this would be the function h1 of x. Okay, if I wanted to have, so I have one of these functions for every one of the nodes. So for example, for the last node, I would just go down to 0 and stay there. So that would be hn of x. So the h's are called hat functions, or sometimes they're called tent functions. And they are non-zero, so hk is 0. I should have said x. hk of x is 0 if x is less than tk minus 1, or x is greater than tk plus 1. So in fact, these hat functions satisfy 3 conditions. First of all, they are piecewise linear. Second, hk at tk is 1. And third, hk at any other tj is 0. So that's enough to completely determine each hk. These last 2 conditions together make hk what we call a cardinal function. cardinal just means it's 1 at one point and 0 at all the others. Now, if you just think about it in general terms, these two conditions, number 2 and 3 together, actually look a lot like columns of an identity matrix, right? One of the components is 1, all the others are 0. And in fact, it has quite a bit in common in some ways with an identity matrix. One of the nice properties that follows right away from numbers, well, from all three properties above, actually. So one of the nice conclusions is that determining the coefficients in this linear combination is trivial. We just use, these are the data values. So that is the piecewise linear interpolant. And really that just follows by checking it. A linear combination of piecewise linear functions is also a piecewise linear function. So P is piecewise linear. And then because of the cardinality conditions, it's pretty easy to show that the sum collapses into a single term at one of the nodes. So the set of hat functions is called a basis. It's an interpolation basis. So that term basis really has the same meaning as it does in linear algebra. Every type of object that you can want to find can be expressed as a linear combination of members of the basis. And furthermore, there's a unique combination. All right. So one more piece of business to finish up with piecewise linear interpolants. So suppose now there is some function f of x that provides the data. In other words, yk is actually the value of f at tk for all k. Then, if f has at least two derivatives, we can say something about how accurate this process is. So the statement here is that we have the difference between the function and its interpolant in the infinity norm. Remember, that's the maximum value. Of f minus p over the interval which is between the first node and the last node. Then that's bounded by some constant m times h squared, where h is the max difference between adjacent nodes. As h goes to 0. So the simplest way to think about this is when the nodes are equally spaced, then they have a spacing of h between them each time, and then the accuracy of this approximation, this piecewise linear interpolation, we would call this second order accurate. So if you use twice as many data values, the interpolant is going to be 4 times more accurate. So that's pretty good. We'll see that we can do better. And the other big disadvantage of this piecewise linear interpolant, right, is that its derivative is not continuous. Technically, it doesn't even really exist at each one of those points where there was a node, right? Unless you happen to get lucky and the two join together to make a single straight line. But at this node, you've got, At this node, you've got two different slopes, and so therefore you don't really have a derivative. You have right and left derivatives. So that can be a downside. I mean, it looks kind of jaggedy, and if you were to take a derivative, it would not be very useful. So the next type of interpolant we're going to look at solves both of those problems.